Hello, welcome back to my channel. After a few years of inactivity due to some college activities that occupy me, and also the fact that I am really bad at organizing my schedule, resulting in this channel being inactive for years, for after eternity later. Let's dive right into the topic that we are about to discuss today, which is about spherical coordinates and how to switch from the, the ordinary three-dimensional Cartesian coordinate into the spherical coordinate. It's actually very simple. So suppose that we have a 3D Cartesian coordinate here. Let me gonna use this feature instead to make it easier. The topic itself is actually not complicated, but it's quite lengthy, so bear with me. So yeah, so suppose this is the, as usual, x-axis and y and z-axis. Now, let's say I have a point P here that is located at a distance r from the origin, or we can also call it as the center of our coordinate. Now, what is the um, you know, what is the coordinate of point P based on Cartesian coordinate? Well, suppose we have this tangential angle, let's say it's theta, and then when we project the position factor of r, of P I mean, onto xy plane, this projection will create an angle of, let's say, phi with the x-axis. Well, what are these angles for? We'll see. So if we have these, and we know that the modulus, or we can say the length of this the length of the position factor of P is r, then we can say that the position of P according to Cartesian coordinate is r sine theta sine phi, not sine phi, sorry. Yeah, r sine theta. What is r sine theta, by the way? If you look at our diagram here, r sine theta refers to the projection of this red vector onto xy plane. And then if we project it once again onto the x-axis, then we will have what? So let me just make it clear here. Let me mark this as r sine theta. And then if we project r sine theta onto x-axis, then we will get r sine theta cos phi. I expect you to understand this already because this is just a simple trigonometry. So you should be very familiar with this. So let's write that down. Uh, x hat. So in Cartesian coordinate, the x-axis, the unit vector along the x-axis is called x hat, and then the unit vector along the y-axis is called y hat, and the unit vector along z-axis is z hat. Sometimes people also use this v symbols instead of x, y, and z hat. They sometimes use I hat, j hat, k hat, where each belongs to, as you can see here. So here, for convenience sake, I just use the x hat, y hat, and z hat convention. Now let's talk about the y component of the coordinate of P. So again, we will project the vector r here onto xy plane, we have r sine theta still. However, since we want the y component of the coordinate, that means we have to project this r sine theta onto y-axis. And then we will get r sine theta times what? Sine phi. Oh, sorry. Sine phi y hat. Okay. And now, let's see uh, what will we have for the z component. It's pretty straightforward. So we only just need to project the vector onto the z-axis. Just do only just the projection once, not more than that, right? You can straightly project this onto the z-axis without having to project this vector onto other planes, and then we will get what? R cos theta, z hat. Okay, so this is the coordinate of P if we use Cartesian coordinate. But what if we use spherical coordinate instead? Well, I have to introduce you about what spherical coordinate is all about. So, it's actually for convenience sake, hence we created this system because uh, makes us this will helps us when we are dealing with problems that involving curvilinear surfaces. What I mean by curvilinear surfaces are surfaces that looks like this, right? So suppose you have a sphere or maybe a cone or something like that. As you notice, these surfaces have a curved shape, right? It's not a straight line. So it's curved along the points. So it's not straight at all. So we have to change our coordinate system a little bit, and we have to make sure we can use a coordinate system that will make our calculation less messy. And this coordinate system will help. Okay? So basically spherical coordinate our coordinate system that also has three components, and the first component we call it r hat or radial component, which is the component that has the direction that is parallel to this red vector. So you are moving it like this, right? Moving it outward or inward. And then we also have the tangential direction. We call it theta hat. So tangential direction is the direction where you can enlarge or uh, decrease the size of this theta angle, right? So this is the direction of tangential direction. And we also have azimuthal direction, where basically the direction refers to the direction of rotation of the projection of red vector onto xy plane. So as you can see here, you can move this black vector here along this arc, right? You can move it here, you can move it clockwise or counterclockwise. So that's what we call azimuthal direction. So basically, those three are the components of what? Spherical coordinates. Now, first of all, how can we convert these unit vectors of spherical coordinates into the uh, the unit vectors of Cartesian coordinate? Well, basically, here's an easy way to do it without using what we call Jacobian matrix, there is actually a geometrical way to do so without using matrix. So it will be easier, I would say. So we know that we already have this, the ordinary unit vectors of Cartesian coordinate, x hat, y hat, and z hat. Now suppose we bring this thing here and we place the origin to be at the same location with the center of this Cartesian coordinates unit vectors. So now we will have this as well. And notice that the unit vector of r hat creates an angle of theta with the z hat, and then the unit vector of of phi hat creates an angle of phi with the y-axis, with the y hat. And why is that? Again, simple trigonometry, and I expect you already know this. Okay, and the theta hat vector also creates an angle of theta with the xy plane, right? Now let's see. What is r hat in terms of x hat, y hat, and z hat? Well, as you can see here, we can basically do the same, just like what we did with the vector r here. So what we are going to do is to project r hat onto xy plane, and then project that projection onto x hat and y hat component respectively, and then we also project r hat onto z-axis. I mean z hat. So here, if we project r hat onto xy plane, we have what? Since these are unit vectors, that means the length of each vector is 1. So we don't really have to write that modulus because we don't really care. So the projection then becomes the modulus of r hat, which is 1 times sine theta, right? Now, if we project it onto x-axis or x hat, then we will get what? We will get cos phi, right? Just like what we have with r here. Cos phi times x hat, right? Now, for the y components or the y hat component, we have what? The projection of r hat onto xy plane, and then we will project that once again onto y hat. So we will have sine theta times, if we project it onto y hat, it's going to be sine phi times y hat plus r hat. If we project it onto z-axis or z hat, it's going to be cos theta z hat. So there you go. So this is basically r hat in terms of x hat, y hat, and z hat. Now what about, let's go with theta hat. For theta hat, we are going to be we are also going to project this onto xy plane. So if we do so, we are going to get cos theta, right? And then if we project it onto x hat, we will get same cos phi times x hat. So that's the x hat component of theta hat. And then the y hat component is going to be cos theta, the projection of theta hat onto xy plane, times sine phi, right? Now, since theta hat points downward, yeah, it's kind of point downward. So we can say that theta hat is in the z is in the negative z region. Hence, the z hat component of cos theta hat, I mean the z component of theta hat is going to be negative because it's in the region where z less than 0. So we get minus sine theta set here, right? As you notice here, if I make it, if I zoom in the picture, we will have this, right? So this is xy plane here. Let's see. So we have xy plane here, which is a plane that is expanded by x hat and y hat. And as you can see, since the angle between r hat and z hat is theta by trigonometry, then the angle between theta hat and xy plane is also theta. And by simple trigonometry, we can see that the projection of theta hat onto z hat is going to be the modulus of theta hat multiplied by what? By sine theta. But since z is less than 0, then we have negative sign here. So that's theta hat in terms of x hat, y hat, and z hat. Now what about phi hat? Well, let us zoom in so we can clearly see what's going on. Here, basically, we have the negative x hat, because as you know this, phi hat is in the region where x is less than 0, but it's in the region where the y values are positive, or at least non-negative. And it creates an angle phi with y-axis. Recall the simple trigonometry concept. We will get what? If we project phi hat onto y-axis, we will get cos phi y hat, and if we project it onto x-axis, we will get negative sine phi x hat. So this is basically phi hat in terms of x hat, y hat, and z hat. Notice that it has 0 z hat component. And why is that? Because it lies solely on xy plane. It doesn't hover around. So that means this vector is comprised by 2 components only. So this is basically how to move from Cartesian coordinate onto spherical coordinate or to the opposite. It's very straightforward, but if you still have questions, please don't hesitate to leave your comments here or just contact me directly onto my email, which I will provide on the description below. Thank you for watching and thank you for your attention. Don't forget to like, subscribe, and please share if you feel this video is helpful. Thank you.